large enough that I can see. All right. So what I want to talk today is from M&Ms to mathematics, so how I learned to answer questions and help my kids love math. And so the world is rapidly changing. And so when I was an undergraduate, one of my student jobs was working in microfilm, microfiche. And I don't know if any of you even know what that looks like anymore. And so the question is, what skills are we teaching you? Why are we teaching you these skills? What skills should we be teaching? A lot of it is learning how to think about problems. You are going to have artificial intelligence and other things that will do the tedious calculations for you. Now, there's sometimes advantages to doing it yourself to get a feel, but it's how do we come up with good questions to ask? How do we attack problems like this? And so good advice that I found works well over the years is ask questions. If you're reading a paper, how can you push this further? What are related questions you can ask? Gather data, start looking for patterns. I love to use games to motivate mathematics. My daughter insists that I am never allowed to lie when I describe a game. I can deliberately mislead. So I may try to mislead you once or twice, but I will never lie. This is joint work that began when my son was 4 years old and my daughter was 2 years old. And they are co-authors on the paper, which is joined with some students from Williams. And so I will get to it in a moment, but I believe if I don't hold the record, I'm close for most successful multitasking of anybody in terms of just how many times I get credit for doing the same things. So this is a math paper, plus things I've done in my probability and other classes, plus things I've gone to do with my kids. Okay, so there are not too many prerequisites for this talk. I've actually given this initially to Association of Math Teachers in Massachusetts. I've given this to young kids. So the more math you know, obviously, the more you can do. But really, all I need is the following. Some notion of logarithms. By now, you've probably quickly glanced at the slide, and hopefully everything looks pretty much familiar. The big rule we're going to use is the log of a product is the sum of the logs. I hope you do not get bored during this talk, but if you do, try to quickly prove it and see if you can actually prove the log laws like that. I need a little bit of basic combinatorics. N factorial is the number of ways to order n people when order matters. N choose k is the number of ways to choose k objects from n when order matters. For example, n choose 1 is just n, 4 choose 2 is 6. You might have seen these if you're taking a calculus class, if you want to rigorously prove what's the derivative of x to the n when n is an integer. Okay, just for a little bit of fun in terms of there's patterns all around you that you may not have seen. Hopefully everybody has seen Pascal's triangle. Okay, so the kth entry in row n is n choose k. Any computer scientists here? All right, how do we start counting? Yeah, good, yes, excellent. We start counting with row 0. And so there's the 0th row, first row, second row, third row, and it's from expanding out n to the k. There's a lot of wonderful patterns in here. We could spend, I think, 3 or 4 solid days, or maybe a really long walk, talking about all the properties you have in Pascal's triangle. One really simple one is to just darken every odd number and erase every even number. And if you do this, you start to see patterns emerge. You can do more and more and more, and you start to see a lot of interesting patterns appearing. This is Sierpinski's triangle. I couldn't find a good video on the web that just shows what happens as you add more and more rows and you keep it fixed to a fixed amount. So I actually wrote a little program to do that and then modified it a little bit with one of the Michigan students. All right, so let me describe the M&M game. And this came from a great question my son asked. I'm going to be a little bit careful how I phrase this because this is being recorded. Not all daycares are equally good at intellectually engaging kids. Some daycares may believe that getting a puzzle with 15 pieces would be a great challenge for a 4-year-old. So I would often pick up my kids early. And one day when my son was 4, he asked me, Dad, if you're born on the same day as someone, will you die on the same day? And I thought that was a really good question for a 4-year-old. How do you explain randomness? Now, it's actually very easy for me to explain this to my son because my wife is an identical twin. Look, no, okay. So there's many reasons why that is not a good way to explain randomness to a 4-year-old. If for no other reason, I would not be able to give that talk other than in prison, where I do actually have a colleague, but that's a different story. So the question is, how do you explain randomness to a 4-year-old and a 2-year-old who happens to be around? So we created the M&M game. So everyone starts off with K M&Ms. We had 5 because I had a little packet on me. And we go 1, 2, 3, toss, and you toss a fair coin. And if it lands as a head, you eat an M&M. If it lands as a tail, you don't. And you keep doing this until you eat all your M&Ms. And I love this is 13 years later, and my daughter still remembers when she got 5 straight heads and got to eat all of her M&Ms as fast as possible. Do you notice anything about the M&Ms of Kayla's the first column, Cam is the second, Steve is, that's me, is the third? Do you notice anything? Good, there you go. We're all starting off with the same number. You could actually handicap and you could give somebody more M&Ms or fewer M&Ms. I'm older, so maybe I have fewer. What else do you notice about the M&Ms? Remember, I'm doing this with a 4-year-old and a 2-year-old. They're different colors, right? Do you think it matters that Kayla got all the blues? Let's not answer that because this is being recorded. At the time, it might have mattered to certain people as to which color M&Ms they got. And there may have been negotiations that's okay, you can get the blues, but I want to be able to have an alternating pattern of red and orange. When we're analyzing the game, does that matter? No. So you always want to think which parts really matter when you're doing the model. So what are natural questions you could ask about this game? There's participation here. So what are some natural questions? I'm sorry? Okay, so how many M&Ms do you want to play with? And so let's say I tell you we're playing with 5 M&Ms or 6 M&Ms. What's a good question to ask?
Is there a strategy that
well, there's really no strategy because we're just tossing the coin. So you could change the game to have a strategy. And then that would be a great thing to do. What if you have a strategy? Maybe if you get ahead, you can eat, and if you delay, then if the next one is ahead, you have to eat 3. So there's a hit. But if it's a tail, then you survive. So all of a sudden now you have a new research project. So trying to tweak this and make it into a strategy game, that's a great way to go. So one thing is, what if the coin is not fair? The original thing is you're trying to figure out what's the probability of a tie. That could easily change as a function of the probability of the coin. As the coin gets more and more likely to be a head or a tail, what do you think happens to the probability of a tie? If the probability gets closer and closer and closer to 1, what do you think happens to the probability of a tie? Yes? Yeah, it should go up. And the question is, how quickly does it go up? How rapidly does it converge to 100% chance of a tie? How long do you have to wait until everyone is dead? This may be, so this I know is a sad way of phrasing this. When I was describing this to one of the grandparents of one of my kids' friends, she actually writes children's stories and she wanted to use this, but she didn't like the death. And unfortunately, negotiations broke down because this is how the game was. You can use Cheerios if you want to do something with life. All right, so here is a plot of the probabilities of having the tie with 1 M&M, 2 M&Ms, all the way up to about 20 M&Ms. So you start off with a 33% chance of a tie with just 1 M&M for each person, and the more M&Ms you get, the less likely it is to have a tie. That's reasonable. We could gather more data. We can go up to 110. I gave this at the 110th anniversary of the Massachusetts Math Society. And then the natural question to ask is, well, where will we be in 110 years? Where do you think 220 would be? So can anybody roughly tell me about what is the probability of a tie with 110 M&Ms? Ballpark. .03. It's about 3%. That seems reasonable. What do you think it's going to be at 220? Okay, so you think it's going to go down a little bit. Do you think it's going to eventually go down to 0, or do you think it's going to have some kind of, it's always going to be above a certain critical threshold? As you get more and more M&Ms, do you think it becomes less and less likely for there to be a tie? Good.
I mean, if you had, like, if you're
2 billion M&Ms.
still not 0.
Still not 0, but the Michigan endowment has decided, that it's going to buy M&Ms. Do you think that as you get more and more M&Ms, the probability is going to get closer and closer to 0? Or do you think it's going to stabilize and then doesn't matter how many M&Ms I have, there's always going to be at least a 0.00004% chance of a tie? So how many people think it's going to stabilize? Right, so we got a few people who say stabilize. How many people say it's going to go to 0? How many people do not know? Perfectly fine. What could we do to try to get more intuition? Eat some M&Ms, and we actually have some play. So we could actually play this. And then we can do a 100,000 step challenge and work off the M&Ms. So I actually ate a lot of M&Ms earlier today just to make sure that they were good. They are. All right, so we could gather some more data and see if we can see some patterns. And so I don't know about you, but it's very hard for me to extrapolate this very well. Now, there were two pieces of information we started the talk with that I want you to know. One of them is very useful right now. Anybody know which one is useful right now? There are two prerequisites to look at this data. Yes, logarithms. So how many of you have seen logarithms in some class? Your hand should be up by now. You know, at some class you should see. How many of you have heard why we care about logarithms? Not as many hands, some, which is good. So one reason we care about logarithms is we can look at things that span many orders of magnitude on one plot. But also a lot of relationships that are complicated become much simpler if we do a logarithmic change of variables. And so if I look at a log-log plot, what kind of curve does that look like? Straight line. And there are procedures that will give you the best fit straight line. We calculate the best fit straight line, or better yet, the computer does. And it gives us a prediction for the log of the probability of a tie as a function of the log of the number of M&Ms. Well, we can then unwind that and get the probability of a tie as a function of the number of M&Ms k. And we can see that it is decaying, and there's an interesting decay constant for the exponent. And we can plug in where we should be at 220. And we get about 1.27% is the prediction. The actual answer is 1.37%. Is that good or bad? It depends. It's not horrible. Both are giving you a small number, but I'm off by about 10%. So it's a significant error percentage-wise, but it's detecting that it's a small number. Can anybody give me a reason why it's doing a bad job? Any thoughts? How could we do a better job? Yes. Yeah, the line is an inexact fit. What's causing the line to have trouble? I'm sorry? Which points curve upward? The ones inside. What could we do? Not derivative. Yeah, ignore them. Right, throw away the data. That the very first few bits, if things haven't settled down yet, don't put too much weight in them. Right? We haven't hit the limiting behavior yet. We have a discrete process. And so with a few things in the beginning could be very tough. So let's just get rid of them. Let's just look at the data from 50 to 110. If you look at that, I will zoom in. I can do this on the iPad. You can see that nice, red line going essentially right through all the points. All right. I would say that's a pretty good fit. And if we do that, we now get a new best fit line, which is a little bit different. And we get 0.01344 instead of 0.01347. Phenomenal. And this just gives you some of the power of being able to do some basic modeling. It doesn't tell me why that's the answer, but it allows me to make a prediction. So then the question is, can we prove why this is the answer? And so what I want to do is I want to talk to you about several different ways you can prove this. And so I love using problems like this as springboards to mathematics. So you're going to see some, at least what I think are some really good math concepts coming into play. So I am old. Can anybody identify the two basketball players? Larry Bird and Magic Johnson, yes. Okay, so they're playing a strange game of basketball. The first one to make a basket wins, and they always have the same probability of making basket. Bird always makes the basket with probability P. Magic always makes the basket with probability Q. They never get tired. Their probabilities never change. They keep shooting until one of them makes a basket. And they always alternate Bird, Magic, Bird, Magic. And because I am from Boston, which is where Larry Bird played, Bird gets to go first. Okay? So we want to calculate what is the probability that Bird wins. So let's call it X. Can somebody tell me how you could calculate the probability that Larry Bird wins? How could Larry Bird win? So give me a way that Larry Bird could win the game. Yes. Makes first round shot, good. And the probability that happens is P. How else could Bird win? Yes. Okay, Bird misses. Other dude misses, yes. You know, anybody who's not a Celtic, doesn't really matter who they are. I like this. I like this. Yes. And then makes the second one. So it's 1 minus P, 1 minus Q times P. How else could Bird win? Yeah, just keep going. You know, this is Michigan. We don't have to go through all the steps, right? Miss, 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 hit. And you just keep going like this. So the probability that Bird wins on the nth shot is each person misses n minus 1, and then Bird gets it. And what's nice is these are going to be mutually exclusive, and they're going to cover all possibilities. And so we have to just sum all of this up. And so the probability that Bird wins is this infinite sum. Well, every term has a P, so I pull out a P, and there's the geometric series. So if we happen to know the geometric series formula, we'd be done. For now, I want to pretend we don't know the geometric series formula, and I want to show you how you can use this basketball game to prove the geometric series formula. Okay? So much of mathematics is about doing something two different ways, one way hard, one way easy, and then say, oh, well, the hard way is now equivalent to the easy way. So let's solve this without using the geometric series formula. So the probability that Bird wins, he could win on his first shot. So X is equal to P plus something. And X is the probability that Bird wins. So if Bird is going to win, if he doesn't make the first shot, then Magic has to miss as well. That's 1 minus P times 1 minus Q. At this point, they've both missed and Bird has the basketball. What's the probability from this point onward that Bird wins? No, P is the probability that Bird wins on the next shot. What is the probability that Bird wins from this point onward? X, right? X is the probability that Bird wins the game starting with the basketball. Once they've both missed, it's like we've reset the game. It's a memoryless process. So now we have a finite equation. Instead of having an infinite sum, I have a finite sum. I'm much better with finite sums. Yeah, this one I can do. And so for simplicity, we're going to let R be 1 minus P times 1 minus Q. So we get X equals P plus Rx. Okay, that's not that hard to solve. So when you do the algebra, you get X is P over 1 minus R. But from the previous slide, we know that X is equal to P times the geometric sum. So therefore, the geometric sum has to just be 1 over 1 minus R. Now, does this work for all values of R? What values of R have we proven this for? Ah, good. So we don't know about this for negative R because R is the product of two probabilities. R is between 0 and 1. Could R actually equal 0? What would it mean for R to be 0? Yes. So P could be 1. How else could R equal 0? Q equals 1. So we would have to think a little bit about whether or not R equals 0 makes sense. If R is between 0 and 1, everything is fine. As a nice exercise, I'll leave it for you to show that knowing that this holds for R positive and less than 1, you can also get for R negative between negative 1 and 0. As a nice exercise, you can tweak this and make that work as well. All right, so we have the infinite geometric series formula. This is the power of finding the right perspective for a problem. It's a memoryless process. We can bypass this infinite sum. Right. This should probably have some application to the M&M game, given that that's what this talk is about. So how does this apply to the M&M game? Well, there's many ways to solve the problem. The first is the overwhelm it with brute force algebra. And I'll explain in a moment why this infinite sum is the answer for the probability of a tie with both people starting off with K M&Ms. All right, so we will see very shortly that this is the answer, okay? Does anybody want to evaluate this infinite sum? Can you look at this infinite sum and see the k dependence? Can you see even that this is going to 0 as k gets large? Well, it turns out that this actually simplifies, and I'll put that in quotes, to the special value of a hypergeometric function. And so if you know hypergeometric functions, again, okay, is there a better way to look at this? Well, where did this formula come from? So I promised you I would show you where it came from. There's 4 events that could happen. And they're all equally likely because it's a fair coin. They both eat an M&M, just Cam, just Kayla, or neither. And so what I'm really doing is I want to calculate what's the probability that the game ends in n tosses. If it ends in n tosses, the last toss has to be a head for both of them. The probability of that is 1/2 times 1/2. And then in the first n-1 tosses, Cam has to have exactly k-1 of them be heads. If the n-1 choose k-1. Same thing for Kayla. And then the 1/2 to the n-1 is just coming from each coin toss. So that's where this formula comes from. Does anybody know a way to convert this process from this infinite sum with 4 possibilities to a finite sum with 3 possibilities? What can I get rid of? Which possibility can I ignore? Any thoughts? When we were analyzing the Bird and Magic Johnson, if they both missed, it was like it didn't happen. So what can we do here? Yeah, when neither eats, it's like that doesn't happen. So we can ignore that case. There's only 3 possibilities. They both eat, just Cam eats, just Kayla eats. We don't record every time we get to tails. And so when we do that now, it's a finite game. Because no matter what, every toss, at least one M&M is eaten. And so when we do it that way, I'm not going to go through the algebra. You never do algebra in public. You get, it's not pleasant, but it's now a finite sum. And you give me a k, and I can very easily calculate what the answer is. Okay. There's another way to do this. Why do you think I'm going to let Cameron's number of M&Ms be C and Kayla's be K? Somebody has to say it. It's the first letter of the names. Choose variables that have good names. Who knows what cosine is? Who knows what 1 over cosine is? What's 1 over cosine? If you were choosing names, would you have cosine go to secant and sine go to cosecant? Do you know why they do it that way? There is a reason. And if you know the reason, it makes sense. If you don't, you're like, why would they choose notation like this? You want notation where you can quickly glance down and see what's going on. So I'm going to use C for Cam and K for Kayla. One of 3 things always happens. So I can view this as a graph. And I really didn't care enough to do a really nice graph. This was done in Microsoft Paint over a decade ago. So I'll start off with 4 M&Ms for each and look at all the different possibilities and just flow down. And if I want to have them end up dying at the same time, eating their last M&Ms together, I really don't want this to be taken out of context. They have to get to which point first? Has to be 1, 1. Because the only way you can get to 0, 0 is from the point 1, 1. So I just have to calculate what's the probability they get to 1, 1. And then once you're at 1, 1, there's a 1 in 3 chance that you get to 0, 0. So I just have to figure out if I start with 100% the probability at 1, 1 and I flow down, what's the probability I end up at 1, 1? So I start off at 4, 4, and then I have 3 possibilities. I can go to 4, 3, to 3, 3, or to 3, 4. Each one happens 1/3 of the time. So after one level of flowing, this is what my probabilities are. Now I can look at those 3 points and see how those probabilities of 1/3 flow. And so I'll start off with the 2 edges, and then the 4, 3 can go down to 4, 2, 3, 2, or it could go over to 3, 3. Similarly, the 3, 4 could go down to 2, 3, 2, 4, or could go over to 3, 3. So the probability for 3, 3 could go up a little bit initially, but then it's going to go all the way down and everything will be one level lower. And you can just keep playing the game and just seeing how the probabilities flow. And just, the calculation is not too bad to do. And eventually you'll get the probability that you end up at 1, 1. And this is a small little delay from when I toggle here to when it toggles up there. And you get 245 over 729 to get to 1, So if we multiply by 1/3, we get 245 over 2,187, or about 11% chance if they both start with 4 M&Ms. Okay. If you looked at the very first title slide very carefully, you would see that in addition to being the director of the small program at Williams, I am also the president of the Fibonacci Association. Yes, there actually is a president. I think at least 2/3 of all mathematicians must be members of the editorial of the association board, just by quick data counting in here. Very, very powerful organization. So you have representation on this campus if you have any concerns about the golden mean or related numbers. All right. How many of you have not heard of the Fibonacci numbers? Excellent. So our schools are doing well. Everybody has heard of the Fibonacci numbers. There is a beautiful formula. This is one of my favorite formulas in all of mathematics, Binet's formula, that gives you an explicit form for the nth Fibonacci number. The Fibonacci numbers are defined trivially. It's the sum of the previous two, starting with either 0, 1, or 1, 1. It's not hard to calculate Fibonacci numbers, but it's time consuming. Binet's formula allows you to jump to wherever you want. What can you tell me about the Fibonacci numbers? What kind of numbers are they? Integers. So when you look at this, if there was a police lineup, and you had to identify the integer, would you notice that you've got divisions by 2, you've got square roots of 5, everything cancels. So it's a nice exercise. What can you replace the 2s and 5s with and still have this always be an integer? All right, so this is a closed form expression that allows you to jump to any Fibonacci number. We can talk later if people are interested as to how do you solve a recurrence like this and come up with a closed form expression, which is wonderful because it lets us know how things are changing, how things are growing. We love closed form expressions. It turns out we have a recurrence for the M&M game. Let's let XCK be the probability of a tie when you start off with Cameron with C M&Ms and Kayla with K. I claim that we have this recurrence. 1/3 of the time, Cameron eats, Kayla eats. 1/3 of the time, just Cam eats. 1/3 of the time, just Kayla eats. And this recurrence will then give us the probability of a tie when they have CK M&Ms in terms of 1 or 2 fewer. So if we start off by knowing the probability of a tie for a small number of M&Ms, we can use this to build up. So if they both have no M&Ms, we will say that it's a tie. If Cameron has an M&M and Kayla doesn't, or Kayla has an M&M and Cameron doesn't, we'll say that the probability of a tie is 0 because one of them is dead and one of them isn't. And so we know what x00 is, we know what x01, and we know what x10 is. We can now use this to find x11. And so we can just march down. Now, what if we hadn't seen this recurrence? Well, if we hadn't seen this recurrence, we would have hopefully seen the recurrence with 4 terms. And what do you notice is on both the left side and the right-hand side? XCK. So noticing that XCK is on both sides, we subtract and we get 3/4. We then multiply by 4/3, and now we get the recurrence. So what's nice is if you hadn't noticed the nice recurrence, that there was a memoryless process, if you tried to do the algebra here, it would be telling you maybe there's something going on. So just really nice thing to ponder and think about. So the question is, how do you solve a recurrence like this? This is a 50-minute talk with pizza coming, so I'm not going to go into how do you solve recurrences with 2 indices and not just 1 index. But there are ways to do stuff like this. We can also just write an Excel program, a Google Sheet, simple code. As long as K is not too large, we can just march down. So x00 would be 1. We can use this to calculate x11, and we get x11 is about a third. Not about, x11 is a third. And then we can use this to calculate x21 and x22, and we can just keep marching down like this. So again, this is really easy for a computer program to do. I don't need to have that finite sum anymore. I can just march down and calculate it like this. I'm going to skip building cases with Catalan numbers. I'm going to just jump to the following. I will put this up for you to ponder. These are the probabilities of a tie for the first 8 values of K. What do you notice? Any patterns? So there's lots of patterns here. Does anybody see anything worth commenting about? Okay, well, I heard somebody say power. Yes? Somebody was saying something with the word power. Power of 3. What do you notice about the powers of 3? So 3, 27, 81, 21, 87, 19, 683. Yep, these are all powers of 3. Can you tell me which power of 3 you have? How do you get from one to the next? How do we get from 1/3 to 5/27ths? 1/2. So we multiply by 1/9. How do you get from 27 to 81? 1/3. How do we get from 81 to 2187? By 3 cubed. Yes. Okay, so the next denominator is what? So the previous denominator multiplied by what? The exponents add. So you get from 1/3 and 1/27th. We multiplied them. Interesting. So does that hold for all 8? Okay. So the comment was that one way you can get this is you multiply the 2 previous exponents and get to the next one. So the data here might have one of the classic mistakes. It's not wrong, but remember how I said I'm allowed to mislead you? What might have accidentally been done to some of these fractions? I might have accidentally simplified. And by accidentally, I might mean deliberately, right? So when you're trying to detect patterns like this, you've got to be very careful. I don't want Mathematica to be simplifying things like this. Because if it simplifies, you might miss something like this. Now, there is this wonderful inspirational, let's multiply by 3 to the 2k minus 1 to clear denominators. That's the power of 3 that works. And so when you look at simplifications and whatnot, this is what's going to work. And you can get the sequence 1, 5, 33, 245, 19, 21, and so on. Have any of you ever seen this sequence before? Okay, you're at least honest. I would be shocked if anybody had ever seen this sequence before. What you do is there's this beautiful website called the Online Encyclopedia for Integer Sequences, the OEIS. If you do not know about the OEIS, you should. When I was a postdoc at Brown, I actually gave a talk on how to write papers using the OEIS. How many of you have had to prove things by induction? How many of you have had to prove things by induction when you don't know what you're proving? Much harder, right? If they tell you what to prove, frequently proofs by induction are not so bad. And so what you can often do is if you put a sequence of integers into the OEIS, it will tell you all the sequences it knows that start that way. And so when I plug that in, it turns out it is sequence A084771. And when you plug that in, it then starts giving you all the information it knows. It gives you references, it gives you generating functions, it gives you explicit formulas when it can. And now all of a sudden, if you have an idea of what you're trying to prove, that makes it a lot easier. And so I did not initially have a sequence of integers, but I did after clearing the denominators. So a lot of times, even if you don't have integers, if you have rationals, you can still use the OEIS very successfully. All right. So for the last few minutes, I want to talk very briefly about some of your future work and takeaways. So I was at a conference at Texas State, I guess just before the summer started, and I was talking with a colleague who has his own summer REU program. I've visited them for many years, so I know his daughter. And so we were chatting, and she was asking, well, what happens if you toss many coins at the same time? What if they have different denominations? And so we started playing with this. Of course, not while people were talking. We gave our full attention, of course, to all speakers at all times, like you are all doing. And what if some of the coins have positive values? What if some of the coins have negative values? So I talked earlier about the Polymath Junior program, where It's entirely online. As long as you've taken one theory course, if you are still an undergraduate in your summer 2025, you're exactly the target market we're looking for. If we have space, we're often able to take people who have just gotten their degree as well. And so we've had hundreds of people working. So I had some students working on projects related to this over the summer. And so they've got a couple of results related to something like this. One of the simplest ones you could ask is there a difference between having a +5 and a -3 and a -2 versus a -5 and a +3, +2? What if you have different starting values? Does it matter how things go? And so in between sessions of the talks, and it was definitely not when someone was speaking, I wrote some very simple mathematical code to simulate what would happen, to start trying to get a feel. So what do you think will happen? So imagine I have a 5, a -3, and a -2. And I flip all the coins at the same time. If the 5 coin comes up with a head, I add 5 M&Ms. So I can now actually gain M&Ms. If the -3 ends up with a head, I take away 3 M&Ms. If the -2 ends up with a head, I take away 2 M&Ms. So what do you think happens on average? So what do you think happens on average to the number of M&Ms per turn? I don't gain them. So if I start at 1,000, do you think I'll ever hit 0? Or do you think if I start off at 1,000, I'm going to be safe? It would be unlikely, but so if I wait long enough, do I expect to eventually be negative? I expect my average to be 0. But over time, what do you think is going to happen? And so here's a simulation. Anybody notice anything interesting about the plot? I'm sorry? Yes. Right. Well, part of that is because I'm only showing every 10th in the later part. So I'm deliberately, because the way Mathematica works, the longer your list is, the longer it takes to process things. And so I started only displaying, from a certain point onward, I wasn't displaying as much data. And all of a sudden, it goes down really fast. Now, this is one data point. If this was the marketing department, business program, then that would be more than enough to extrapolate from. But mathematicians, we want more than just one data point. Do you think this is always going to happen? Do you think that you're going to get up and then you're going to uniformly go down like this, or do you think it might be a more wide pattern? How long do you think it's going to take? So this took 120,000. We started off with 1,000, and we had coins +5, -3, -2. So we've got a lot of different things varying here. We have the initial starting value, and we have the amount of the coins. I want to know how long do I expect it to take as a function of all those different parameters. So there's a lot of random processes going on here. There's a lot of wonderful probability going on here. And these ideas of probabilistic models can be used for a lot of interesting pure number theory problems as well, to just try to get a feel for what's going on. So in a problem like this, I do expect that I will eventually go to 0. And I can even predict how long it should be, and roughly how many tosses it should be as a function of what my initial value is. So just some final takeaways. You should always be asking questions. So whenever you're at a talk, there's a couple of questions you can always ask. What happens if you remove that hypothesis? What happens if you increase the number of dimensions? Can you give me an example? It's amazing how many times you have theorems where people can't give you an example of anything that satisfies the conditions. But try to ask questions when you're seeing something. Remove some conditions and see what happens. There's often more than one way to solve a problem. I assume everybody knows your rival school in football. Can anybody give me the official name of your main rival? No. Historic. What is the name of the historic football rival of Michigan? The Ohio State University, right? In mathematics, we don't talk about the proof. What do we say in mathematics? We say a proof. There's more than one way to prove things. And often different ways of looking at things, different proofs will give you different insights. And so we saw several different ways of solving the M&M problem. We saw a memoryless process. We saw a hypergeometric function. We saw a walking on graphs. We saw a recurrence relation with two indices. Different ways of going to generalize better or worse. A couple of years ago, I had a small student and we were doing a problem in additive combinatorics and we were bumping it up to higher dimensions and the results we were getting were terrible. We were trying to extend a paper that a previous group of mine had done, and the extension just wasn't working. And I said, maybe the problem is we're trying to extend the current best result in the subject. And that's using very specific, very powerful techniques. Let's go back to the very first paper in the subject. And it turns out that that was the paper that extended to higher dimensions. And so you've got to be very careful about what methods are you using, how you're looking at problems. Another one is looking at data the right way. I am a huge fan of doing log or log-log transforms. It's a great way to try to sniff out patterns. There's so much data coming at us, trying to figure out which things really matter. How can you look at it and try to see the right relationships? Frequently, we don't know where the math is going to take us. Always be open, keep an open mind when you hear things. This could be the start of a new problem. I have some students at Williams right now who I've been talking with about some job interview problems. And some of them are really interesting. And it's not just good mathematics, but it's also how would you program this in a reasonable amount of time? Computers are getting more and more powerful, so it's not as important. When I was young, my dad splurged and he bought the 16 kilobyte RAM extension for me. That was a treat. 16 kilobytes. And so you get a little bit spoiled when you have very powerful computers, but there are still some problems where we don't have that many data points. And it's very easy to try to extrapolate in a range where we should not. So we only had one data point for this, 5 minus 3 minus 2. Do we really want to make any conjectures from that? And then what I'll end with is one of my favorite quotes. If all you have is a hammer, pretty soon every problem looks like a nail. There are two ways to look at this. One way is it doesn't matter what you're asked. If you're good at using a hammer, you will convert it to a problem where you can use your hammer. I will risk saying this with this being recorded. How many people have ever watched a political debate? To some extent, it may not matter what question is asked. You have an answer that you want to get to, and you're going to just find a way to get to that, to use your hammer. If you are really good at a certain technique, I'm going to try to convert whatever problem you give me to something where I can use my technique, because I can do that, I'm good at that. That's one way to look at the quote. What I want to leave you with is another way of looking at this quote. Go to the land of the screwdriver. If they could have solved the problem using a screwdriver, they would have. They're smart people. I don't want to compete head-to-head with Gauss in number theory. My freshman year in college, my study group had a discussion who would be better in the group, me or Euler. And I was the only one who didn't vote for Euler. I said, Euler's dead. And they go, yeah, but we think it would be really motivational to have Euler's body here. And, that was hard to hear. If I go up against the greats using the techniques they have, I'm not going to make much progress. I could get extremely lucky, but odds are I won't. If, however, I go and I use techniques that are not used in that subject, so I've written papers in marketing where I've used combinatorics that I've learned from analytic number theory. These are not techniques that people in the business school typically have. And so I've worked in so many different areas. This is one of the advantages of a math program, is you're learning how to be problem solvers. And so I strongly encourage you, pick up lots of different things, learn the different techniques and perspectives from the different subjects, and then always be thinking about how can you apply what you're good at in a place where people are not as familiar with that. And so that's a good place to end, and then happy to chat more over pizza or pre-pizza.